Welcome to Graphing Trig Functions. We are going to start with the graphs of cosine and sine and learn a little bit about them, talk about amplitude, period, phase shift, and vertical shifting, and then do some examples. Then briefly, to end the video, we will take a look at the parent graphs for the remaining four trig functions. So let's get started with f of x equals cosine x, the parent graph for the cosine function. In order to find out what the general shape of this graph looks like, we are going to take a look at the unit circle in order to create a basic t-chart for 5 main points on the graph of f of x equals cosine x. Those 5 main points are the ones we've been using. Radians 0, pi over 2, pi, 3 pi over 2, and 2 pi. Yes, there are 4 spots, but technically 5 different locations, 0 and 2 pi being the same place. So let's start. If we plug in 0 into our function, cosine x, our output is 1 because the cosine of 0 is 1. Following that same pattern, plugging in pi over 2 for x, the cosine of pi over 2 is 0. Then pi, the cosine at pi is negative 1. At 3 pi over 2, our cosine is 0. And at 2 pi, we have come full circle, literally, and we end with the same output of 1. Let's take a look at what this looks like on a graph. What I have here is a trig coordinate graph, and that's because we don't have like integers for x values here. We instead have the common radian measures. We can see that we go both left and right. So we'll focus from 0 to 2 pi here, since that is how long it takes for the cosine graph, the parent graph, cosine x, to complete one full cycle. So I'm just going to simply graph these. I do need to mark some y values on here. It looks like the minimum output we have is negative 1, whereas the maximum output is in fact 1. So I'm going to go all the way up here and all the way down here, keeping it symmetrical, just so we can see the graph a little bit better. So let's first graph these coordinate points. 0, 1 up here. We have pi over 2 comma 0. We have pi negative 1, 3 pi over 2, 0, and 2 pi comma 1. Connecting these dots, they are not going to be linear. It's going to be kind of smooth and a little bit curvy. And this is one full cycle of the graph of cosine x right here. Now, how about these points in the middle? This would technically be the halfway point between 0 and pi over 2 right here. That would be pi over 4. The cosine of pi over 4 is root 2 over 2, which as a decimal is 0.7. And so this is approximately 0.7. Here, the cosine at 3 pi over 4 is negative root 2 over 2, or negative 0.7, and so on. So these are the 5 main points on our cosine graph, starting at 1, going through 0 down to negative 1, back up to 0, and ending again at 1. Next, let's take a look at the parent function, f of x equals sine of x, and let's graph this curve here, or this periodic function. And in order to do that, we once again are going to use those 5 main points. Recall that those 5 main points are 0, pi over 2, pi, 3 pi over 2, and all the way back to 2 pi. Now, I'm not going to bring the unit circle up for this one. We can think about it in our heads, or if you have a unit circle for reference, that's also great. The sine at 0 is 0 this time. The sine at pi over 2 is 1. The sine at pi is 0. The sine at 3 pi over 2 is negative 1. And the sine at 2 pi is 0. Graphing these 5 main points will have 0, pi over 2 comma 1, pi comma 0, 3 pi over 2 comma negative 1, back to 0. So connecting these dots here, again, it's curved. They're not linear by any means. And that is one cycle of the sine curve. The cosine curve and the sine curve actually are the same if we shifted them left and right a little bit, but note that they do start at different points. The y-intercept of the cosine function is up at 0, whereas the y-intercept of the sine curve that we just saw is at 0 at the origin. That is a huge difference that helps most students kind of decipher which is which, because they do have the same general shape. As you can see here, it's as if we started here and then went up, and this is really the cosine curve right there. So they are extremely related. This again is one full cycle of the sine curve, and it takes 2 pi. If we think about the unit circle, it takes 2 pi radians to go one full time around the unit circle, and that is why for the parent functions sine and cosine, their period, their length of time to complete one full cycle, is 2 pi. Okay, here's kind of a boring slide right here, but I did want to give the definition of a periodic function. Both cosine and sine, as well as the other trig functions, are periodic because they repeat after one full period. Basically, what's happening is if we can plug in a certain point, and then if we added some x value and we still got the same thing out, that's a periodic function. Meaning if we added 2 pi, we'd still get the same output out. It's like going around the circle and ending up at the same spot. So both sine and cosine are periodic functions because of their repetitive nature. Some properties of these two functions that we've just graphed, if you take a look at both of our graphs that we just saw, both of them have a domain of all real numbers. Now that we can see both of them, we saw that we could plug anything we wanted into each one of these functions. However, their outputs were restricted. We can never have a cosine or sine value that is less than -1, nor can we have a cosine or sine value that outputs greater than +1. And if we take a look at the unit circle, that is because the radius of the unit circle is 1. So our ranges for both of these functions, their parent functions, just cosine and sine of x, are -1 to 1 inclusive. They are both continuous and smooth, which we can see. The cosine is an even function and the sine is an odd function. And we can see that just visually, if we kept going with our cosine function, it is symmetrical about the y-axis, whereas the sine function is actually symmetrical about the origin. It's not symmetrical about the y-axis. Both of them, as we've previously discussed, have a period of 2 pi. So the parent functions of both of these, we haven't seen any shifting yet. The parent functions cosine and sine of x both have a period of 2 pi, meaning that that is how long it takes for them to complete one full cycle of their graph. After 2 pi, they would just repeat that same formation or same cycle again every 2 pi. What if both of the times that we graphed the sine and cosine functions previously, we kept going? Because these are functions that keep repeating, they're periodic. Our cosine function, as we can see, is in green. It has a y-intercept of 1, and we only graph this part of it right here, but it keeps repeating. We can see that clearly to the left, it keeps repeating as well. Then our sine curve, which we graphed next, has a y-intercept of 0, as we can see here, and we only graphed one cycle of it from there to there, although it does keep going. So these functions are periodic, and they look like the output on a heart rate monitor. They are waves. They are also called sinusoids. Let's take a look at some of the features of these periodic graphs. This is one cycle, and we can see that from the baseline, which a lot of times is the x-axis, up to the maximum point on the curve, that is called the amplitude. It's like the height of the wave. Then we can see that a period is the length along the x-axis, or whatever our baseline is, that it takes for a function to complete one full cycle. Normally this is 2 pi, but we are going to see some ways in which we can either shorten or lengthen the period of a sine or cosine graph. Another feature that we'll see with these graphs is called a phase shift. And a phase shift is shifting one of these functions horizontally left and right. Now we can take a look at, let's say we took a look at the cosine graph. How can we make the cosine graph exactly the sine graph? I mean, they are the exact same shape. They're just shifted away from one another. Well, if we moved this point on the cosine curve over pi over 2 units, and we did that with all the points on the cosine curve, it would lie flat on top of the sine curve. And we can see that the cosine and sine are really just a phase shift of pi over 2 units apart from one another. We just talked about amplitude, period, and phase shift. These are 3 of the 4 main features of any of the periodic functions here, sine and cosine, that we've been talking about. Well, for any omega is greater than 0, these are the ways that we can write the functions out Do not panic, it looks scarier than it really is. These are just certain ways of writing cosine and sine graphs that have been shifted, stretched, and moved about from their original parent graphs, just cosine x and sine x. Note that out front of each one we have a capital A. That means that is the amplitude. Now sometimes this A value might be negative, and so that's why the amplitude of the cosine and sine graphs is going to be the absolute value of A, the lead coefficient. The way that we figure out the period, or how long it takes for one of our curves, cosine and sine curves, to complete one full cycle, is we take 2 pi, the original period, and divide it by omega. Omega is this coefficient of x inside here. Then, in order to find the phase shift, we take phi, another Greek letter, which is what we're adding or subtracting in here, in this case what we're adding, and we divide it by that omega. In order to determine if we have a vertical shift, that is what is added or subtracted at the very end. Let's take a look at an example. Let's take a look at this example here in green. We can see that we have y equals 3 times the sine of 4x and then plus 1 on the outside. So we are going to be having an amplitude other than 1. Since we have an a value other than 1, we are going to have a period other than 2 pi because we have some omega value here, the coefficient of x, that is not 1. And we are also going to have a vertical shift, this plus b on the outside. The only thing we don't have in here is this plus phi right here. And we don't have that, so that means we're not going to have a phase shift. Let's start with the amplitude. The amplitude is the absolute value of the lead coefficient A. In this case, our lead coefficient is 3, and the absolute value of 3 is still 3. The next thing that we'll find is the period, the length of time it's going to take our graph to complete one full sine cycle. Well, this is affected by this coefficient of x here, omega. Normally, it takes us 2 pi to complete one full sine cycle. But when we have a number in front of x here, this number, if it's greater than 1, is going to speed that up. We're going to be able to complete 4 sine cycles within 2 pi. So our period is telling us that it's only going to take us pi over 2 to complete one of them. Let's see how I got that. I'm following this formula here and taking 2 pi divided by omega. Omega is 4. So we're going to do 2 pi divided by 4, which is pi over 2. Again, this is telling us it's only going to take us pi over 2 on our graph to complete one full sine cycle. Earlier, it took us 2 pi of a length to complete one full sine cycle. And in this case, we're now going to be able to complete 4 sine cycles within 2 pi, meaning each one is only pi over 2. The next thing that we'll take a look at is the vertical shift, since we've established we don't have a phase shift here. So our vertical shift is just that plus b. So in this case, since we have a plus 1 at the very end, our vertical shift is a plus 1. The first thing I'm going to do is just ignore the vertical shift. We will just do that at the very end. So for right now, I'm just focusing on this part right here. I'm focusing on the amplitude and the period. We have established that the 5 main points of our sine curve are starting at 0. They are 0, 0, pi over 2, 1, in this case it's 3, back down to pi at 0, 3 pi over 2, negative 1, in this case negative 3 because of the amplitude, and then back to 0. That is one full cycle of the sine curve. We've already graphed that. In this case, we're still going to do that, but it's going to be smushed. We are going to do that in only pi over 2 length. So we are going to take this original graph of the sine of x and squeeze it so that it finishes right here instead of all the way out to 2 pi. Wow, that's going to be kind of tight. Let's try it. We have to establish the halfway, a quarter, and then another quarter. So we have our 5 main points. Boom, 2, 3, 4, 5, where we end. When we graph those, we remember that the main idea with sine is that we start at 0, then we go up to our maximum, back to 0, down to our minimum, and back to where we started. So this is the sine curve. It's just smushed because now its period is only pi over 2, meaning we can do this 3 more times to get to 2 pi. This 4 here tells us we could complete the sine cycle 4 total times in 2 pi now. Okay, so now we've taken care of the amplitude and the period. Note that the amplitude is not something difficult to take care of. It's just about labeling on your y-axis correctly. The period is the harder part. The vertical shift is also not that difficult. It just means that everything's going to be shifted up by 1 unit here. So doing that, I can do that very simply on here and just shift everything up 1 unit. Now, can we make this graph look a little bit nicer and not have it so smushed? Sure. If you are doing this on your own and not having to smush it onto a pre-made graph, what you could do is just go out as far as you need. So our graph went out to 2 pi because that's kind of the norm. In this case, let's make our graph go out to where we want, pi over 2. So I'll go out to some arbitrary point, put pi over 2 because that's how much I need to graph. Then I'll pick a halfway point and label that appropriately. In this case, it's pi over 4. Then I'll pick my other halfway point or quarter points in between. You can choose to label those if you want. In this case, they would be pi over 8 and 3 pi over 8. Then we can easily graph it from here. I put my amplitude on here, and then I'm going to graph those 5 main sine points. Sine starts at 0, goes up to its maximum point, back to 0, down to its minimum point, and back to 0. The final thing that we take into consideration is that vertical shift. And in order to do the vertical shift, we move all 5 points up 1 unit. So I will do that in yellow. So we'll move this coordinate point up 1, this one up 1, up 1, up 1, and up 1. So this is what our final graph looks like. That is 1 cycle or 1 period length of this original graph here. So yellow is our final. Let's take a look at another example. We have y equals the cosine of x minus pi over 2. So our amplitude, the number out front, that is just 1. Our period, in order to find the period, it's 2 pi and divided by omega. Omega is the coefficient of x. In this case, the coefficient of x is 1, and so therefore our period is 2 pi. Our phase shift is negative phi divided by omega. And in this case, our phi value is actually negative pi over 2. Since our phi is negative pi over 2 and our omega is 1, we are doing negative pi over 2, which is actually a positive pi over 2. Then we can see that we don't have a vertical shift here because there's no plus or minus after the closing of the parentheses. So there's no vertical shift. We don't have to worry about moving our graph up or down, like in the previous example. However, in this example, we are going to have to move to the right, pi over 2 units. So the first thing I'm going to do is actually ignore the phase shift and simply graph the function with amplitude of 1 and a period of 2 pi. Hey, that sounds like the original cosine graph. It is. Really, the only thing different from the parent function here is this phase shift. So let's just sketch the graph of the cosine of x, which is the one with amplitude 1 and a period of 2 pi. So we're going to have our 5 main points. For cosine, we start up at 1, go down to 0, down to negative 1, back to 0, and back up to 1. Now in order to do this, we do actually have to make sure that we label on our axis here, our y-axis. Again, I'm just doing an arbitrary number of ticks to be 1 and negative 1. If I put it here and here, our graph would just be so smushed and small. So I'm spreading it out. And then to graph this, again, the cosine at 0 is 1, our 5 main points here. Cosine at pi over 2 is 0. At pi, it's negative 1. At 3 pi over 2, it's 0. And at 2 pi, we've gone full circle. So this is this right here, using an amplitude of 1 and a period of 2 pi. That is the original cosine graph. It's the parent function. Now, to graph this phase shift, we are going to be moving everything pi over 2 units to the right. Now, how do I know if it's left or right? Well, if you've done the phase shift correctly, a positive number means right and a negative will mean left, which is kind of confusing because looking at the function here, we have x minus pi over 2. If you recall from previous discussions of shifting horizontally, it's sort of the opposite of what you'd think. X minus a number means move that amount to the right, whereas x plus a number means move to the left. So we're actually going to move all 5 of these points, pi over 2 units, to the right. When we do that, This coordinate point here, moving pi over 2 to the right, will now be at pi over 2 comma 1. This coordinate point here will move pi over 2 to the right, and it will now be at pi 0. We'll do the same thing for the other points. And then this last one actually has to move pi over 2 to the right, which would actually make us have to extend our x-axis, and this coordinate point, adding half a pi, is 5 pi over 2. Graphing this final function here after our phase shift looks like this. So our final graph is the one in pink. In this next example, let's graph y equals negative sine of 2x. Our amplitude is, again, the absolute value of the leading coefficient. Here our leading coefficient is -1, and therefore our amplitude is 1. Period, the way we find the period is 2 pi divided by omega. Omega is simply the coefficient of the x. So our coefficient here of the x, our omega value, is 2. So to find the period of this specific function, we do 2 pi divided by 2, and the period is pi. That means it's going to take pi in order to complete one full sine cycle. Now our phase shift is entirely dependent on if inside the sine or cosine function in the parentheses we have a plus or minus of some value. We do not. Therefore, we do not have a phase shift here. And then a vertical shift is after the closed parentheses if we have a plus or minus at the end. We do not, so we have no shifts here. So I'm actually going to graph 2 cycles of this graph here, of this function, because it's going to take us pi in order to complete one cycle, and that means we can complete 2 sine cycles in 2 pi. That's what this 2 here means, how many cycles we can complete in 2 pi. Each one takes pi. So I'm going to put just a dotted line here just to show that that is where the ending of our first sine cycle will be. So our sine cycle has 5 main points, we recall. The sine starts at 0, goes up to 1, back down to 0, down to -1, and then back to 0. And we have to do that in this length here, from 0 to pi. So we have our halfway point. We also have our quarters here. In this case, it's pi over 4 and 3 pi over 4. I'm going to mark those a little bit darker just so we know. So these are our main 5 points here. All right, then I need to go up to 1 and down to -1 since our amplitude is 1. Now, again, I'm not just going to go to 1 and to -1 here so we actually can see our function better. I'm just going to go up 4 units, call that 1, and go down 4 units and call that -1. Now we're ready to start graphing our first cycle. We're going to begin at 0 since that's where the sine begins. Then we're going to go up to 1, back to 0, down to -1, and back to 0. We have completed one full cycle. Some of you might be saying, but wait, isn't there a negative here? Dun dun dun, there is. That means that once this is graphed, we actually need to flip it. It's going to be flipped fully. Now, what does flipping look like? Well, flipping 0 means nothing. Flipping means reflecting over the x-axis. All of our outputs are reversed. So instead of starting at 0 and going up to 1, we're actually going to start at 0 and go down to -1. We're actually going to reflect over the x-axis and be opposite of what we are. So my final graph here is going to be in green, and reflecting it will look just like this. That's taking care of that negative out in front. Now I don't want to have both graphs there in the end, so I'm going to just erase the pink graph. So all that negative did was reflect over the x-axis. It made our outputs the opposite of what they were. Now I have graphed one full cycle of this. Since the cycle is pi, the period's pi. I'm just going to keep going though. Why not? We have the space. We can just repeat that. So we can do it again since we have another length of pi here. So we once again have our halfway point between our cycle and our quarter points and then our ending point there. So our sine begins at 0, begins here. Then, because it's negative, it's going to go down to -1, back up to 0, up to 1, and back down to 0. Then we will connect in a curvy and not linear way. And we have actually graphed 2 cycles here of this curve. y equals negative the sine of 2x. Next, we are going to move on to the other 4 trig functions. We are going to just explore these in a more surface level way and not get super in depth with phase shifts, amplitude, and all that. Let's take a look at y equals the secant of x. We know that the secant is actually the reciprocal of cosine. So we are going to use our knowledge of the graph of cosine in order to graph secant. Once again, we are going to graph at our 5 main coordinate points, those starting with 0 through pi over 2, pi, 3 pi over 2, and 2 pi. We'll add more if necessary. Now, in order to find the secant, what I like to do is just find the cosine at those points and then take the reciprocal. So the cosine at 0 is 1, and the reciprocal of 1 is just 1. Therefore, the secant at 0 is also 1. Then at pi over 2, our cosine is 0. The reciprocal of 0 is undefined. So this is actually undefined. We can write it as UND or just like that. Then at pi, our cosine is negative 1. The reciprocal of negative 1 is also negative 1. So the secant at pi is negative 1. 3 pi over 2, the cosine 0. And we have the same situation as we did at pi over 2 with an undefined secant value. Then 2 pi, our secant is again 1. Let's see what this looks like. Well, this is what I've come up with. Not anything spectacular or really anything graphed. We really only have 3 coordinate points, and we actually have 2 vertical asymptotes. We have vertical asymptotes because at pi over 2 and at 3 pi over 2, our secant is undefined because we're dividing by 0. Therefore, that becomes vertical asymptotes. So we can write over here that when we are undefined, we end up getting a vertical asymptote. And secant is undefined when cosine is 0, since 1 over 0 is undefined. Well, how can we figure out what the rest of this graph looks like? It's not just 3 coordinate points. One option is to plug in some other values. So those other values would be right here as pi over 4, 3 pi over 4, basically the pi over 4 family. Let's try that with secant. So at pi over 4, our secant is the reciprocal of cosine. Well, the reciprocal of root 2 over 2 is just root 2, which is approximately 1.4. Then at 3 pi over 4, which is right here, our secant value is negative root 2 or negative 1.4. So it's somewhere down here. Then at 5 pi over 4, right here, our secant value is the same. It's negative root 2. At 7 pi over 4, our secant value is positive root 2 or positive 1.4, somewhere around here. If we continue doing this, we would see, and also because secant, like cosine, is an even function, meaning it's symmetrical about the y-axis, we can see that what happens is we get these little arcs here. And they alternate going up and down, just like this. It also is periodic, and it keeps repeating. As we also go more to the left, at negative pi over 2, which is the same place as 3 pi over 2, we again have a vertical asymptote, same with negative 3 pi over 2. So every half a pi, beginning at pi over 2, we have a vertical asymptote. This means that our vertical asymptotes are any line with the equation x equals pi over 2, our first one. Then, since going pi to the right, and if we keep going multiples of pi to the right or to the left, that means we can add on k pi, where k is an integer. Another main thing we talked about in this video is the period, or the length of time it takes for the function to complete one full cycle. Well, the period of the secant graph is how long it takes for us to complete one sort of work through of the pattern. If we look, our pattern is an upward facing parabola and then a downward facing parabola and then upward again. It looks like it took us from negative pi over 2 to 3 pi over 2, this entire length, to complete one of those cycles. This entire length right here is 2 pi. So the period of the secant graph is 2 pi. Cosecant is the reciprocal of sine, and so when we are filling out our main 5 points here again, what we can do is find out what the sine is at each one of these main points and then take that reciprocal. So the sine at 0 is 0, and therefore the reciprocal of 0 is undefined. So we're going to have a vertical asymptote to start. Then at pi over 2, our sine is 1. The reciprocal of 1 is 1, therefore the cosecant at pi over 2 is 1. At pi, our sine is again 0, and its reciprocal will result in a vertical asymptote on the graph of cosecant since it's undefined. At 3 pi over 2, our sine value is -1, and its reciprocal is also -1. So the cosecant at 3 pi over 2 is -1, and at 2 pi, again, our cosecant is undefined, causing a vertical asymptote. Let's put this on the graph. Well, here's what we have, and it looks like every time we are at a pi, a k pi value, we have a vertical asymptote, and every time, well, when we're at pi over 2, our cosecant's 1, and at 3 pi over 2, our cosecant's -1, which we found. Then at negative pi over 2, which is really the same spot as 3 pi over 2, our cosecant is again -1. And then at negative 3 pi over 2, which is really positive pi over 2, our cosecant is +1. This graph, in a similar way to secant, looks the same. So it is of the same form here, and it has these, it's a parabolic form in between every 2 asymptotes. This is what the graph of cosecant looks like. So much like the graph of secant, the graph of cosecant has vertical asymptotes. They are vertical lines, so their equation in this case is x equals, they begin at 0, so we don't have to write 0, but then they repeat at every k pi. So we'd have another one at 3 pi, 4 pi, we'd have other ones at -1 pi, -2 pi, -3 pi, and so on. So every k pi, where k is an integer, we have a vertical asymptote. Does the graph of cosecant have a period? Yes, it does. Remember, a period is how long it takes for this graph to complete one full cycle or begin repeating itself. If we start here at 0, we notice this upward parabola right here. Then in the next one, we have a downward parabola. Next, we would have an upward parabola if we can take a look at our pattern. Therefore, in order to complete this entire cycle, or its entire one time through of its pattern, it's taken 2 pi. So the period of this graph is 2 pi. Next, let's take a look at the graph of y equals the tangent of x. We again have our 5 main points. Recall that tangent is sine over cosine or y over x. So at 0, our sine or our y is 0 and our cosine or x is 1. 0 over 1 is 0. At pi over 2, our sine over cosine is 1 divided by 0. So essentially, it's undefined there, but essentially anytime we have a cosine value of 0, our tangent will be undefined, since that would make 0 in the denominator. So here, we have a vertical asymptote. At pi, our tangent is 0. At 3 pi over 2, our tangent is undefined, giving us a vertical asymptote in the graph, and at 2 pi, our tangent is again 0. Here's what we got. We also can see that the symmetry of this at negative pi over 2, which is the same as 3 pi over 2, we again will have an undefined tangent, and in a similar way, we also will have a vertical asymptote on our graph of tangent at negative 3 pi over 2. Then once again, our tangent at negative pi is 0, and our tangent at negative 2 pi is also 0. But what about the spots in between? How about if we check out the tangent at pi over 4, 3 pi over 4, negative pi over 4, all of these in between values here, which are pi over 4 family. At pi over 4, our sine and cosine values are the same, so our tangent is 1. At negative pi over 4, our sine is negative root 2 over 2, but our cosine is the positive root 2 over 2, so our tangent's -1. Then at other values, at 3 pi over 4, our tangent, or our sine and cosine are opposites, therefore a tangent again is -1, and so on. So we have a couple points here. Let's figure out where we want 1 to be on here. I'll put it right here. And then we can graph pi over 4 comma 1, and negative pi over 4, negative 1. At 3 pi over 4, we're again at negative 1. At 5 pi over 4, we'll be at 1. We can see that we have sort of the same thing happening at each one of these spots here. But it's not going to be linear. We're not just going to draw a straight line through these 3 points, and we know that because a vertical asymptote is something that this graph will end up approaching. The way that tangent ends up looking is sort of like a little curve, and almost like the x cubed function in the middle. It almost looks cubic right here. So the tangent function is periodic, it repeats. And how long does it take for one cycle of the tangent graph to complete? Well, it looks like the tangent repeats over and over again in between every one of these two vertical asymptotes. What is the length, or what's the distance between any two vertical asymptotes? Well, from 0 to pi over 2 is pi over 2, and from 0 to negative pi over 2 is another pi over 2, so this entire length right here is 1 pi. Therefore, the period of the tangent graph is pi, and then there are vertical asymptotes as well here because we're going to have vertical asymptotes in any trig function where the denominator has a potential to be 0, which it does with tangent. So there are vertical asymptotes, it looks like, starting at x equals pi over 2, and then they repeat every plus or minus a pi. So plus k pi, where k is an integer. The last trig function is left up to you, the student. So based on everything we've learned so far in this video, for y equals the cotangent of x, make an xy chart like we've done in order to graph, or get a general idea of what the graph will look like, then identify the period of the cotangent, then finally write the equation of all the vertical asymptotes. Remember that is going to be involving the value k, where k is an integer. Go ahead and pause the video and try all of this, and then once you're ready, hit play to see how you did. Here is the graph of the cotangent of x. Note that it has many similarities to the graph of the tangent of x. They are reciprocal, so that does make some intuitive sense. The periods are the same in that the periods of the tangent and cotangent are only pi, whereas the periods of sine, cosine, cosecant, and secant are all 2 pi. Here we again have vertical asymptotes, but they are at a different location than the tangent graph, just because cotangent is the reciprocal, so it's not all the same. The vertical asymptotes occur at every k pi, where k is an integer, so 0 pi, 1 pi, 2 pi, negative 1 pi, and so on. We can see that in between any two vertical asymptotes is one cycle of the cotangent graph, which is essentially a flipped version of the tangent graph. You were able to figure this out by knowing that at every pi over 2, the cotangent is 0, and at some of the pi over 4 family, our cotangent values are the same as the tangent values. They're either 1 or negative 1. The rest sort of comes into play with understanding the general shape of the tangent graph. In this video, we explored the graphs of these 6 trig functions. We went pretty in depth with the sine and the cosine and did a lot of different shifting with different graphs, getting away from their parent graphs. The other 4, we just took a look at the parent graphs. For all 6, we talked about the period of the parent graph, as well as for these 4, the equations of their vertical asymptotes. We saw that the period of these 4 parent graphs right here is 2 pi, whereas the periods for tangent and cotangent is only 1 pi. The most important thing we learned is sort of how to figure this out on our own by making an XY chart and using our unit circle to figure out what these graphs look like. Nice job.